If a diamagnetic solution is poured into a U-tube and one arm of this U-tube placed between the poles of a strong magnet with the meniscus in a line with the field, the level of the solution is. It is said that a diamagnetic solution is there in a U-shaped tube, and one end of this is in a magnetic field. So what happens is here, this is diamagnetic solution. So it will move from stronger field to the weaker field. Since here it is stronger, the field is stronger, so it will move away from here. So the meniscus will fall down. So correct option is option B. The material suited for making electromagnets should have. We know that electromagnets means a coil is there and soft iron is inside, mounted inside, because this soft iron is having low retentivity and low coercivity. So for making temporary magnets, we use soft iron because it's having low retentivity and low coercivity. That means whenever we switch off the current, that is when we remove the external magnetic field, its soft ions magnetism also comes to zero or very less, and it has low coercivity, means its magnetization, this material will have a magnetization and its magnetization should come to the less value by applying a reverse current to the coil. So option B is the correct one. And for making permanent magnet, the material should have high coercivity and high retentivity. And materials used for that are steel, cobalt, alnico, etc. Two identical thin bar magnets, each of length L, pole strength M, are placed at right angles to each other with north pole of one touching the south pole of the other. So they are arranged like this. North pole of one touching the south pole of the other. So this will have a magnetic moment downwards and it will have a magnetic moment towards the right. So these two will have a resultant magnetic moment that is equal to root of m square plus m square, that is root of 2m square, that is root 2m. And this magnetic moment is actually the product of pole strength into length. So correct option is option C. Two similar bar magnets P and Q, each of magnetic moment M, are taken. If P is cut along its axial line, Q is cut along its equatorial line, all the four pieces obtained have. Options are given. It is said that two bar magnets are there. One is cut along its axial line and another is cut along its equatorial line. Here magnetic pole strength become half, whereas length is same for both the pieces, but here magnetic moment is same but length became half now after cutting. So for P, magnetic moment equation is pole strength into length. Here after cutting, magnetic moments changed for each half. Here pole strength is m by 2 and length is L only. So it is ml by 2, or ml is Paul's magnetic moment, so it is m by 2. And for the next one, Q, again magnetic moment changed after cutting, so it is pole strength into length. Here pole strength is m, length is L by 2 now, so it is ml by 2. We know that ml is magnetic moment, so it is m by 2 again. So all the four pieces will have magnetic moment m by 2. Option C is the correct one. A magnet is parallel to a uniform magnetic field. If it is rotated by 60 degree, the work is 0.8 joule. How much work is done in moving it 30 degree further? Equation 4, work done is mb cos theta 1 minus cos theta 2. Here first of all, the magnet is parallel to the field. So it is mb into cos theta 1 is, when it is parallel, theta 1 is 0 minus cos, when it is rotated by 60, theta 2 is 60. That is mb cos 0 is 1 minus cos 60 half. So it is mb divided by 2. And the work done is given as 0.8 joule. So mb is 2 into 0.8, that is 1.6 joule. Now again it is rotated by 30 degree further. So work done is now mb into cos rotated from 60 minus cos, now it is 60 plus 30, that is 90. Theta 2 is 90. So it is mb into cos 60 is 1 by 2, cos 90 0. So it is mb divided by 2, that is mb is 1.6 divided by 2, that is 0.8 joule, or when we convert it into erg, that is 0.8 into 10 raised to 7 erg. So correct answer is option A, 0.8 joule or 0.8 into 10 raised to 7 erg.